Hello folks. Last time I was up here, I was talking about IPv6 and addressing and some challenges there. And one of the things that I had to do was try to convince people that IPv6 is a thing and that people actually use it. And I thought this time I'd give you some concrete examples of how you may already be using it right now. Show of hands, how many people have a smart home thing in their house? It may not be that smart, but some kind of Wi-Fi attached device. Okay, now keep your hands up if you think that it works well and these devices all play nicely with each other and you're just thrilled with your smart home ecosystem. Okay, yeah, that's nobody. So the reality is that all these things don't play nicely with each other. I've got this really smart garage door opener, but I couldn't tell Siri to open it until I installed Home Bridge and all that kind of stuff. So it's all a mess. And in response to that, a little bit of history, there's this thing called the Zigbee Alliance, and they had a project Connected Home IP project. And then they became the Connectivity Standards Alliance, and CHIP became renamed Matter because that name makes sense. And Matter was launched and supported by Apple and Amazon and Google and Comcast and a whole bunch of people. You know, Amazon obviously gets you Ring and that ecosystem. Apple and Google get you both devices, handsets, and operating systems and smart home devices. And I'm not sure why Comcast is there, but okay, we'll go with that. And the important thing is that Matter uses a protocol called Thread. Well, I don't know if it's a protocol suite to communicate with all these low power IoT, oh, hello. There we go. Smart home devices. So what is Thread? It's a specification that's supposed to handle low power, secure, wireless IPv6 communications for connected home products. So basically, it's going to sit there right in the middle. Matter sits up there at applications. This sits down here. And it's supposed to handle onboarding, providing secure communications, all that kind of stuff between your smart home devices and whatever clouds or devices that you're using to control them. So Thread has a lot of features. Devices can be full thread. That's stuff that's probably going to be plugged in and on all the time, or minimal thread. That might be something like a temperature sensor. It's not going to be on all the time. It's going to wake up every once in a while, tell you what the temperature is. There are thread routers that are supposed to handle things because maybe not every thread radio can hear each other thread radio, so it may require some mesh or some other technologies. There are border routers that can handle how these devices talk to other PHYs like Wi-Fi or Ethernet. And with all of this, we have a lot of IPv6 going on. You can have link local addresses with the interface identifier based on 802.15.4. We'll talk about that in a second. Mesh local EIDs with the interface identifier chosen randomly. A routing locator, that's a thing. Don't worry, we've got 10 minutes, not going to go into it. And a global unicast address, which can be SLAAC or DHCP or manually assigned. Refer back to the previous talk about that. Quick reminder about 802.15.4. It is a low-rate wireless personal area network protocol. There's one little weird channel in Europe. I don't even know what's up with that. That's just kind of insulting, I would think, if I would live there. And then about 10 channels in 900 megahertz land and 16 channels in 2.4 gigahertz. They do peer-to-peer or point-to-point type technologies as well as a star topology. One thing that's really cool is they can be synchronized or unsynchronized, and in synchronized networks, they have a guaranteed time service that gives you a contention-free window to send super frames. So the idea of not having to worry about contention is cool, although there are unsynchronized networks, and those also have the same contention avoidance technologies that we're kind of used to. And it supports using these EUI 64-bit addresses, or in a personal area network, you can use a 16-bit short address. Okay, great. So is there any problems? Well, the IPv6 minimum MTU is 1280 octets, and the 802.15.4 maximum physical layer packet size is 127 octets. So much like me trying to fit into a coach airline seat, that's not going to fly. Oh, and by the way, that's physical layer packet size. Once you put in the layer 2 headers, you have 80 octets of payload. So we're a little short. Now, here comes 6LoWPAN. I know that sounds like the name of a Mortal Kombat boss. No, it's an actual protocol. It's actually the name of a working group. It's been around since about 2003, I think. Original RFC draft came out in 2007. And it's basically, it provides an adaptation layer for how do we carry IPv6 on this low bandwidth, very constrained network. It gives you some ways to handle the addressing. It utilizes a lot of shared context to do header compression. We're going to talk about that in a second. It's my favorite thing about this protocol. And it also handles fragmentation and reassembly because you're often very not going to be able to fit your whole datagram into a single 802.15.4 frame. So, quick reminder about how an IPv6 address works. We have 64 bits of network address on the left and 64 bits of host address on the right, also referred to as an interface identifier. So if you're using an 802.15.4 64-bit address, well then you're good to go. You have your interface identifier. Just use that. If you're using that 16-bit short address, our goal is to get to a 48-bit number that is then put through the same process that a MAC address is when generating an address via Slack. So you either slap a bunch of zeros on it, 32 zeros on it, or 16 zeros plus the PAN ID, which unfortunately isn't always present, and that gets you to 48 bits. You turn around, there you go. You've got your 64-bit interface identifier. So header compression is where things get very interesting because the idea is, do we really need the entire IPv6 packet header? And the answer is we don't. We know some things. All the devices are on the same PAN. You're not going to be communicating to something on a different personal area network. So that means that we're always using link local addressing. The PAN is only on a single IPv6 link. So if you just, even if it's not link local addressing, it doesn't matter. The network identifier, you don't need it. You can figure it out. The addresses, the interface identifiers, you can figure that out from the L2 information because we just kind of went over how you do that. So because you know how to compute the address, and I know the L2 address of the person that sent me the frame, I can reconstruct the IPv6 source and destination address information in the packet header from the frame header. And the packet size, same thing. You know the header, the PPDU size from the L2 information, you just reconstruct it. So when all of that is done, you can take the header from 40 octets to 2 octets. And that's 20-to-1 compression just by doing some math and figuring some things out from what we already know. So this is how this is going to work. And it's probably already working. There are already several Thread devices. If you have a HomePod Mini, that speaks Thread, although only with other Apple devices at the moment. All of the Eero routers, I believe, are Thread enabled. So this is already possibly happening in your house. If you have Nest Secure smoke detectors, that's how they talk to each other. And if one of them is having problems with its Wi-Fi, it doesn't need to talk to the internet because one of the other Nest Secures that will also talk to the internet. So this is a lot to try to squeeze into 10 minutes. So what I would suggest, if you find this all interesting, if you're going to be studying any of the IoT certifications, the Thread white papers are very helpful. They lay down everything from how they use 6LoWPAN to just overall network structure. OpenThread is an open source thread implementation that Google has released. You can put that into a Docker instance and play with that to all you want. And then, of course, there's RFCs for days. They're all right there. If you start with the 6LoWPAN RFC, you'll find the rest of them. They all lead from there. So that's all I got. Hopefully you found it interesting.